Chapter 1 starts, like all chapters in this book, with a mathematical overview. And in this chapter, the summary of what you are supposed to be learning here is that functions, there are many different kinds of functions, but you should be able to describe them graphically, algebraically, numerically, and verbally. That concept runs through the entire book. Section 1, the objectives are written right there. Work with functions that are defined graphically, algebraically, numerically, or verbally. And in class, we did that with this one, the archery problem. We said that somebody was standing on a cliff and shot an arrow. Where was the arrow after these many seconds? How far was it after these many seconds? How did it possibly get to be negative feet high? That kind of thing. So in other words, this story about an archer on a cliff can be told as a story verbally, can be told algebraically if you wanted to create an equation for it, or graphically as you see below. So then we get to types of functions. And the idea here is for you to be able to make connections among the algebraic equation for a function, its name, and its graph. In other words, if I show you a graph, you should be able to tell me what kind of function it is. And if I name a function, you should be able to show me what the graph ought to look like. And in fact, just jumping ahead here for a minute, these problems right here, name the type of function that has the graph below, that's what I'm talking about. But you should be able to do those. In order to prepare you for that, we cover the definition of a function. And that should not be news to you. But the definition of a function is that it's a relation. And then all of those words show up here: ordered pair, relation, function. They're all sort of related to each other. A function is a specific kind of relation where for every input there is only one output. If I give you x, you can tell me what y is without hesitation and without any confusion. In this graph, that would be easy to do, because everywhere along here where there's an x value, there is only one y value. This graph, not so much. If I stop here and say, what's the value of the function when x is this much, you might say 0, you might say this much, or you might even say this much. And you would be right, but a function can't have 3 right answers. Okay. There is something called a vertical line test, which does exactly what I just did with my finger. That is, move it along here. If at any point the vertical line touches more than one point on the graph, warning bells go off. Okay, this is not a function. All right. And we talked about terminology. Probably, certainly you've all seen the notation before. The one word that you probably didn't have before was argument. The argument of a function. That's the input value, whatever you're putting into the function. And then what the book does is give you a whole variety of types of functions, identifies them for you, shows you representative graphs, gives you a verbal description, tells you some features. A polynomial function, that's sort of the generic thing. It's important to know that the graph crosses the x-axis up to n times, and it has one less than that number of vertices. In other words, points where the function changes direction. And then there's direct variation, which Here's a straight line that goes through 0, 0. Power function, right here, so-called because we are raising x to a power here. So you've got power functions, you've got exponential functions, and that's the one where the variable actually shows up as an exponent. Okay. And you have inverse variation functions, where you wind up with x in the denominator. The idea of a Boolean variable is a construct in order to tell your calculator to restrict the domain of a function. So, for example, if I wanted you to draw this function, I would say, here's the equation, and I want you to draw it over the domain 0 to 4. And you would be able to do that. Those are not the kinds of instructions that calculators understand. We want the things that are outside the domain to not exist, and the things that are inside the domain to exist. And we have a way of making things not exist. We divide them by 0, and suddenly they're not there. So if you tell your calculator, okay, here's what I want you to do. I want you to take this function, the way I've laid it out here, and then when x, the input, the argument, is between 0 and 4 inclusive, you could be 1, and dividing by 1 has no real effect. And so it'll turn out, it'll be just the way it would have been. If x is not between these two numbers, then make it be 0, which will then force your calculator to try to divide this by 0 and say it doesn't exist and not graph it. Then we went from there to dilation and translation of function graphs. Okay. If I give you a function, you should be able to take it and move it, or stretch it, or compress it. There are some vocabulary words here, image and pre-image. Pre-image is what you have before the translation or transformation. Image is what you have after the transformation. You need to be able to dilate and translate functions, yes. There are two kinds of dilations. You can have a vertical dilation or a horizontal dilation. If you want to dilate a function vertically, you would multiply the entire function by a number. And that number would be the factor of your dilation. If you want to dilate it horizontally by some factor, you would multiply the x, the argument, the number inside the function, the input, you would multiply that by the reciprocal of your factor. And here, the function given by this, and right here is the main version of this, h of x is actually a translated function of f of x, where we've moved c spaces up or down, depending on whether c is positive or negative, and d spaces left or right, depending on whether d is positive or negative. Notice that we're adding this one, we're subtracting this one. Just again, in terms of vocabulary, if you're affecting the argument, that's an inside transformation. And if you're affecting the entire function, that's an outside transformation. Compositions of functions are basically doing two functions, one right after the other. Here are two functions, f of x and g of x. If I put a star in here, it comes out as a heart. If I put a heart in here, it comes out as a hashtag. Now, that means this is true, and it means this is true, but it also means this is true. When I'm doing this, I'm treating this whole thing as one big box, one big function. What happens in here doesn't matter. What goes in here and what comes out here is what matters, and that's the composite function. And the composite function can be written in a number of different ways, the notation of it. Right? Here, you have two functions, a of x and r of x. And the way this is laid out, you find r of x first and then use that as your argument for a. And you can combine them using the little circle here or here. And each one of those different notations means the same thing. One thing about composite functions, when you're graphing them, if you're doing it from a table of values, if I'm looking for f of 1, that would be 3. G of 1 would be 5, but g of f of 3, g of f of 1 would be from here to here to here. Okay? Because the 1 is mapped onto the 3, and the 3 is mapped onto the 2. And the fact that this happens in the middle doesn't matter if I'm doing it as a composite function. Now the thing is, we have talked about functions in a variety of ways, as a relation, as a set of ordered pairs, as a graph. There is another way to think about them, and that is as a mapping. And so this textbook describes your the composite functions in terms of mapping values one on top of another. And in terms of the domain and range of the composite function, it's not going to be the same as the domain and range of the original functions. Basically, the domain of the composite function is going to be all the values in the domain of G where the result of G is actually still in the domain of F. This is an example of the kind of problem that you should be able to do, where you're finding values for G of x, or f of G of x, or G of f of x. This is not commutative, by the way. F of G of x and G of f of x are different. And then we have inverse of a function. Now notice there are two things here. Given a function, find its inverse relation, and then tell whether or not the inverse relation is a function. You can have an inverse relation that is not a function. So, for example, this is a function of t, of time, expressed as miles, distance. So I'm saying that for every hour, it's these many miles, and for every 5 hours, it's these many miles, and for every 8 hours, it's these many miles. If I want the inverse relation, all I have to do is turn the chart around. The inverse of this relation of 0.2 is 1, and of 0.6 is 2, and of 1 is 3. And as it turns out, there are no values here that appear twice. If we had a value here that appeared twice, that wouldn't keep t from being a function. But it would keep the inverse relation from being a function. So that's sort of what you have to look for. In terms of notation, this is what inverse function looks like, where we put the -1 up here as an exponent to the f. This does not mean this. Graphically, an inverse relation is going to be a reflection of the function across the across the diagonal line x is equal to y. So if this is my original function, this would be the inverse of it. And if you draw the line y is equal to x between them, you'll see that it's a reflection. Algebraically, the way you find an inverse is literally to turn around the equation. So instead of y being equal to 0.4x minus 0.2, you make x be equal to 0.4y minus 0.2, and then solve for y to find out what function of x would make this happen. Ultimately, what this really is an undo button. An inverse function, or an inverse relation, is an undo button. If I have a function here, and it is f of x, and when I put x in, I get a star out, the inverse function, or the inverse relation, but in this case let's call it the inverse function, would be something that when I put the star into it, an x would come out. So that if I combined these two as a composite function, nothing would happen. An example of that would be x minus 7. That's what we're talking about. And then this would be x plus 7. And if I put this in for x, the 7s would cancel out and I would just have x. Now here's the thing about whether it's a function or not. If you look at this parabola right here, if I wanted to find the inverse relation, I could draw a diagonal line here, reflect this across the diagonal line. This thing here is the inverse relation of this. I could find it by plotting points, or I can find it by graphing. But this is not a function, because this doesn't pass the vertical line test. In fact, you can tell by looking at a function whether it has an inverse function by using the horizontal line test. If a horizontal line crosses it in two places, it's not going to have an inverse function. You could create an inverse function by restricting the domain. If I said only for all x values greater than 0, that would become that. Now that's a function. If the whole function is invertible, then it's a one-to-one function. And when you create a function using a restriction on the domain, that makes it an invertible function within that domain. Definitions and properties. Again, you should know these definitions. Let's talk about this here. Given a function, transform it by reflection and by applying absolute value to the function or its argument. In other words, we've got two more transformations we can do here. One of them is reflection. And you already know some form of reflection. You already know that if you want to turn a parabola upside down, the equation for a parabola, if a is positive, then it's going to look like this. And if a is negative, it's going to look like this. And if a is equal to 0, it's going to be a straight line. You've done that before. Here, we're talking more specifically about taking the function and either making the argument negative or taking the whole function and making it negative. You should be able to tie this in with what you already know about inside and outside transformations. This is an inside transformation, so it's going to affect things horizontally. It's going to be a reflection across the y-axis. This is an outside transformation, which means we're changing the whole thing. So it's going to reflect across the x-axis, because we're changing the y values. And that's why this would become this. Let's do it again here. If I'm using a parabola here, this would become this. Whereas this would become this. Here's where that is in the book. And then absolute value transformations, we're talking about this. These instructions are kind of rough to follow, but you've already done this before, I think. Have you ever graphed this function? Right? What does it look like? Sort of a straight line. It's a V. That's because we're reflecting across the y-axis. X might be positive over here, but by the time you put it into the function, nothing's changed. If you start with a negative x, it's going to have the same value as if the x were positive, right here. And the easiest way I can think of to explain this is to say, all right, if I'm taking the absolute value of my argument, this is going to actually turn into two different functions. One is going to be what happens when x is greater than or equal to 0, and that is nothing. And the other is going to happen when x is less than 0. And that's going to be that. And we just discovered the difference between these two things. Take a look at this function here. This function here, f of x, it is defined over a domain where x is negative. With g, where g is equal to f of the absolute value of x, well, that means this part of f is not going to exist in this way. What's going to happen instead is as soon as you start with negative x's, they're going to behave as if they're positive, and that's a reflection across the vertical axis. If you take the whole function and take its absolute value, well, we're going to have the same thing we had a moment ago, which is if f of x is greater than or equal to 0, then this will just be f of x. And if f of x, which means the y value, is less than 0, then this is going to be the inverse. What does that look like? That looks like this. If you start out with this parabola here, and then you take the absolute value of the whole function, it means that y can't be less than 0. And whenever you have a value of y that is less than 0, it changes to a positive value of equal distance from 0. And last but not least, even and odd functions. If a function doesn't change when you invert the argument, it's considered even. If you invert the argument of a function and it turns out to be the same as if you had inverted the whole function itself, that's considered odd.